Hi everyone. In this video we're going to talk about potential energy, specifically the potential energy associated with gravity and springs. Before we jump into these derivations though, let's talk briefly about the connection between potential and kinetic energy. We know that all energy falls into the two categories of potential and kinetic. Well, what about all the other types of energy? What about thermal energy? Well, thermal energy is just atomic motion, so that's actually kinetic. Electrical energy is a potential energy. Nuclear energy is potential. So all the different ways that we view energy will fall into these categories. The exception really being work, which we dived into in a previous video. And work is when one system acts on another system and expends its own energy to change the energy of something else. So the connection between these, where we convert kinetic into potential, that connection is the work done. Now, we know that in the equation for work, we have the differential change in work is the force dotted with the differential change in position. So we are inherently talking about applications of forces that change the energy quantities. Now, when we look at these forces, when we did the kinetic energy discussion, we talked about how the forces are changes in momentum, and we did a replacement on this. Consider though, we could just take a force expression and we could put it directly into this equation. We could find the amount of work done by a particular force. Now, we're going to dive into this in a later video, but when we talk about forces, there are two different categories that forces can fall into. The first is conservative, and the second we could call non-conservative, or you can call this dissipative. So what falls into conservative? Well, the two that we're going to look at today, gravity and springs, the forces associated with gravity and springs, these are conservative. So what is a non-conservative or dissipative force? Well, that would be something like friction. Friction is going to take a body. So let's say we're doing an example of a shuttlecraft. So here is our shuttlecraft. We have a booster attached to it. It's generating some kind of thrust. Our shuttlecraft can experience all types of forces. For example, it could be we could be launching this out of a gravity well. We could be launching it off of a planet or off of a moon. We could have the thruster, the ablation or expulsion of mass from the booster, generating some thrust, and that could change the kinetic energy of it as well. This thing, consider though, also as it moves through atmosphere, there's drag. So in all of these cases, we're seeing some exchange between potential and kinetic. But what about with that drag though? The drag is going to change the kinetic energy of our craft, but it's not going to increase any kind of potential associated with it. The drag isn't doing any work, causing a change in gravitational potential. Really what the drag does is it just decreases the kinetic energy and turns it into heat in the air surrounding your shuttlecraft. So you have some heat shield on your shuttlecraft, and the air around it is going to get very hot due to the friction. So we have the conservative forces that lead to potential energy expressions, so things like gravity and springs, and then we will have non-conservative forces that only diminish the kinetic energy. How can you calculate the work done by a non-conservative or a dissipative force? Well, go back to the other video where I talk about this topic of just work, and you take your friction or your drag term and you put it into this expression, and then you can solve it through numerical integration if you're doing some kind of simulation. So what we're looking at today is we're looking specifically at conservative forces, and conservative forces are tied to potential energy expressions. Okay, so let's clean this up and let's get started with the first example, which is gravity. To find this potential energy expression, we're going to start with work. The force that we need to include in this work expression is the force due to gravity. So we're going to use Newton's definition of gravitational force. I will call that F sub g, and it is capital G, where G is a gravitational constant, multiplied by m1, m2, these are the masses of the two objects, divided by the distance between them squared. Let's call it r. Now we can make some assumptions, and let's solve for the simplified gravitational potential first. Let's make some assumptions that, let's say that this force due to gravity is m times g. This is probably the form you're most familiar with. We can get this form from the real one if we make two assumptions. Let's say that, first of all, this m that we're talking about, let's say that this is m2, so the mass of your object, and little g is going to equal big G times m1 over r squared. Now this assumption about little g, we're going to say that little g is constant. Well, the distance between some object and another object is changing, right? We're trying to find gravitational potential. So for example, when I lift my eraser, I'm changing its gravitational potential. So this quantity right here, r squared, this is actually changing. We're just assuming that g is constant. And over short distances, this assumption is actually acceptable. You can do some quick math and you can say, take a very low point, take New Orleans, and then take a higher point, take Denver. New Orleans is right at or just a little bit below sea level, and Denver is it's called the Mile High City because it's a mile up. So take the radius of the Earth and then add to it that 1 mile change between New Orleans and Denver, and you will find that there is an incredibly small change in this numerical value of r squared. So for something like my eraser just moving up and down, it's not a big deal. If we want to do something with rockets or satellites or spacecraft, we do need the real expression because in that case, we are traveling significant distances. And we'll come back and we'll do the real expression in just a moment. So we're going to do the simplified one first. Let's take this simplified force term and let's put it into the work expression. Now, when we do that, we also need to talk about dP. So let's say that we have some object and center of mass of this object is point A. We know that it exists in some space with an inertial reference point, an inertial frame, etc. If we keep track of the position of this object, let's go ahead and give it 3 degrees of freedom, and let's track it in the inertial frame. So Q1 x hat in, Q2 y hat in, Q3 z hat in. And we can draw our inertial frame in 3D, there it is. So x in, y in, and z in is pointed up. So what's the differential change in this position vector? So d p in A, you can distribute that differential operator. So this is d q1 in the x in, d q2 in the y in, and d q3 in the z in. Just because it's differential doesn't mean it's not a vector. So don't forget your directions. So let's take gravitational force and let's put it in here, and we're going to take our differential position and put it in as well. Now when we do this, we have to remember that these are vectors and the dot product yields a scalar. So dW equals, the force is m times g, it's a vector and it points down. So gravity is pulling this object down. It's pulling it towards the center of the Earth. So as far as our directions go, it's pulling it in the negative z hat in direction. And then we are dotting now with dq1 x in, dq2 y in, dq3 z in. This dot product operator is going to take care of the directions for us. It's 0 dotted, 0 in the x hat end dot with this, 0 in the y hat end dot with this is going to yield zeros for both of those. So dw then is going to equal, and I'm going to pull the negative to the front, negative mg dq3. Okay, so what's the work done? The work is equal to the integral of dw. So this is the integral of minus mg dq3. So we have minus mg q3. And we could, if we want, we could replace this q3 down at the end. We could rewrite this. And we can say that W, and I'm going to put a G on it, so the work done by gravity, this is equal to minus mg, and we could replace that Q3 with the more commonly seen H. So mgh. Right now, though, it's negative. Why is it negative? Because we're looking at this in terms of a work quantity, but not as a potential energy. The symbols for potential energy, it depends on application. In formal vector mechanics, it's this, it's kind of a script V off at a slant. I prefer to not use this just because it ends up looking like velocity. You may also see potential energy as a capital U. Sometimes this is used for internal energy, which is slightly different than potential. I prefer to use the capital Phi symbol. Greek letter P, so P for potential. You see this one crop up oftentimes usually in physics text or physics papers, things like that. So I'm going to use the Phi. So Phi, we're going to connect potential energy, and this is done at the differential level usually. So this is equal to negative dW. So Phi then is just really equal to the negative of the work. So we have an expression for the work done by gravity. So if I want the potential energy associated with gravity, well, it's just the negative of that, and that's going to yield mgh. So here's our simplified gravitational potential. We know, however, that lowercase g is actually a function of the distance, and in this case, the distance is h. So if h increases, the value of g needs to actually be changing. Consider also if you plot this function, if we treat m and g as constants, then this is a line. Now, I have drawn the line coming out of the 0 point. Consider that we did actually solve this through integration, which means there's an integration constant associated with it. So, interesting thing about potential functions. They always have some integration constant associated with it. How do we deal with that? Usually in these problems, we take all of these mgh's, we take these h values with respect to some kind of datum plane. And we say we're going to establish some line. This line represents the minimum potential energy, and then anything above that becomes a positive energy, and anything below that becomes a negative energy. Usually, when we're working simple problems, we don't like to work with these negative energy quantities. So if your object moves down, that means you just change the datum plane and you redefine h then from that new datum plane. And then now your values become positive. So we just adjust this and then we set the a equal to 0. That's how we end up with these simplified mgh expressions. Now, what about actual gravity? Oh, let's leave our object on there. There you are. Okay. If we want the actual expression, that means we just have to put in the actual force term. So dW is going to equal this actual expression is. Tell you what. Let's write it as. We know that the gravity is going to point down, so I'm going to go ahead and put the negative in front. So negative g m1 m2 over r squared. and then dotted with the D position. We do know that those translations in the x hat end and the y hat end are going to equal 0. So I'm just going to say dot, dot, dot for those first two terms plus dq3 zn. Oh, and there we go. Don't forget the force as a vector as well. All right. So the gravity is in terms of r, and the position vector is in terms of q3. But let's think about the relationship between those. Here's the Earth, and we're going to draw a very much out of scale drawing. Here's our object, and we're keeping track of this object with some displacement called q3, and the actual position of this with respect to the Earth is like that, with respect to the center of the Earth. Consider that if q3 increases a little bit, that means the distance from the center of the Earth also increased a little bit, and in fact they increased by the same amount. There's an offset between these, and let's say that's, excuse me, let's call that some kind of r bar, right? Then if r is the actual distance between the center of the Earth and the center of our object, then r is equal to q3 plus r bar, where r bar is that constant. So dr is going to equal dq3. Because as soon as you take the differential of a constant then is going to be 0. So what we can do with our expression above, we can rewrite it then, and we can say that dw is going to equal minus g m1 m2 over r squared times dr. I have replaced the dq3 with dr since this one's already in terms of r. And since we did dot product, we lose the vector notation. If you're uncomfortable with writing it this way, if you're uncomfortable or not quite as practiced with the integrals, you could write this as minus g m1 m2 over r squared dr. You could write it as r to the negative 2, etc. At the end of this, we're going to get the same answer. So we want the potential energy expression. I'm going to go ahead and put the G on it, so this is the gravitational potential. We know that this is negative of W, so I'm going to, we could take this and we can take the negative of it, which means the negative cancels, and we're going to solve for this by integrating. So the integral of negative, oh, it's not negative anymore, G m1 m2 over r squared dr. This is going to yield. Now, when we integrate this, we're actually going to get a negative. If you integrate this term, it becomes negative g m1 m2 over r plus, again, some integration constant. So let's clean this up just a little bit. Our final expression for gravitational potential. We had the original one, and that was mgh, and now we have the real one. I'll tell you what, I'll put a little star on this one because that's our simplified. The actual gravitational potential is negative cap g m1 m2 over r. And same story with those integration constants. We had some offset. So these look very different, but if you actually plot these, you get some interesting behavior. So we're looking at our gravitational potential on the vertical axis, the horizontal, the x-axis. This is our distance, r. And this term, this is an inverse function. So if you ignore the negative sign for a moment, and we say that g m1 m2 is a constant, this is like plotting a over x. So a is just some constant, and then the inverse function 1 over x. As x gets very small, as r goes to 0, this 1 over x term blows up, and it actually goes to infinity. Well, if we put a negative in front of it, that means at r equals 0, this term is at negative infinity. So our potential function is going to look like this. And as R continues to increase, the gravitational potential is going to decay to 0. Well, that's very different behavior from what we said with the MGH. We said MGH was a line, right? A straight line, and if we don't have any datum plane, then we don't have any, right, if we drop this integration constant where we can just shift it up and down, that's like moving the offset. So, what's the connection between these? Well, we know first of all that the assumed gravitational potential is wrong. In a broad sense, it's wrong. One thing to consider is that MGH is always increasing with h. So as you leave and you get further and further away from the planet Earth or from the moon or from the sun, etc., then not only is your potential always increasing, it's linearly increasing, which we can look at this function and we can see that that's not true. Now, this potential is actually always increasing, it's just asymptotically approaching 0. But it is becoming more positive. So, what is actually happening with this, this assumed is that we're linearizing this nonlinear expression, and we're linearizing it around the radius of the Earth. So if you were to plot this, this function, we could find the point at the radius of the Earth, and we could take the tangent line, and that is our linearization, our one-point linearization for this nonlinear potential function, and this approximation is our MGH. We have just adjusted that this plus A, this offset, we have adjusted plus A, we have brought it down to bring it into contact and to show these two things together. So if you were able to zoom in on this point where the radius that we're looking at is close to the radius of the Earth, if you zoom in on that point, what you will see in a very exaggerated sense, you'll see a straight line, and you'll see the more and more you zoom in, you will see another line that looks almost straight, and it just comes into contact, and then it just slowly breaks away. And then the error, the difference between our two potential functions is the error between these lines, and that error is going to grow with increasing radius. So this is how we find actual gravitational potentials. So if you were simulating spacecraft, it could be planets, it could be satellites, etc. You have a choice when you're going to total up all of your energy quantities. You can either use a gravitational potential that itself is a function of the distance between the two centers. You do not use this simplified equation, or you could calculate the work done by gravity, and you could, if you're doing numerical integration, you could calculate this as the change in work, or the power associated with it, and you could say that this is, you take the gravitational force and then you dot it with the velocity of your craft, and then you can numerically integrate it to find this quantity. And the thing to remember, the connection between these two, when you go to total your gravity quantities, or when you go to total all of your energy, if you want to prove no energy is being created or destroyed, you just have to remember that the work is equal to the negative of the potential. Okay, so that's it for the gravitational potential. Let's clean this up and let's switch gears and let's talk about spring potentials. The potential energy expression that you get for a spring depends on a couple of factors. First of all, are you modeling a linear or nonlinear spring? In reality, all springs are going to be nonlinear. Some will be more nonlinear than others. For this video, we're going to do just linear springs. If you need the potential for a nonlinear spring, you can watch what I do in this derivation, and honestly, if you've made it this far, you can handle the math. What are some other factors? Well, sometimes we use springs to model internal stiffness. So for example, let's say this is a support column and we apply a load to the top of this support column. This column, regardless of the material, will compress just a little bit. This force is going to create a pressure on top. That pressure is actually going to be present. If you were to cut this column, you would find this pressure present at every cross section throughout this column. So this is actually stress inside of this support column, and that stress is going to cause some strain. That strain being a little bit of deformation, and every material is going to deform just a bit. So we could actually model this strain using springs. So suppose that we're using this to, suppose we are modeling stiffness of some material. And if you are interested in looking at how to do this, check out the video on spring mass dampers. So we could model some stiffness, and this is going to affect your potential, because if you're modeling stiffness, then there is no unloaded length. There's no unloaded length of the spring. And when I say unloaded length, let's talk about case number 3. What if you're talking, or what if you're modeling an actual spring, like a literal spring? So instead of modeling something theoretical like the stiffness in a material, what if you literally had a spring in front of you that you were stretching and compressing? Well, that spring, if you were to just set it on the table, that spring would have a standard length. Stop. If I had an actual spring on the table in front of me and I wasn't applying a force to it, it would have a standard length at which it would be at rest. And that's called the unloaded length. If the spring is unloaded, if there's no forces applied to it, then it does not store any energy. So we have this second, third consideration. What if we're modeling an actual spring with an unloaded length? So we're going to do 2 examples. I'm going to do linear springs, and I'm going to do one for modeling stiffness without an unloaded length, and then we're going to come back and we're going to do it for an actual spring with an unloaded length. But there's actually more cases than this. When we do these, we're going to do a mass with a spring attached and connected to a fixed surface. What if you're doing say, the support column, and we want to break this into a series of masses, and we want springs acting between all of these? So that becomes a slightly more complicated problem. What if you're doing a series of literal masses stacked on top of each other, and each of these springs have unloaded lengths? These terms are slightly different than these two because these are dependent now on the motion of 2 objects, as compared to this first case, which is only a function of the first object. So that does play into your final potential term for that particular spring. So by which I mean that this spring on top would be a function of the motion of the block on top and the block in the middle. The spring in the middle would be a function of this block in the middle and then the lower block, and then the lower spring would have a potential term similar to this one. So this is 2 more cases that we could tack onto this list, and we could derive those. But again, if you've made it this far in the video series, and you can follow what I'm going to do for these first two examples with the linear springs, then you could work these more difficult ones, and you could even introduce nonlinear springs. Okay, so let's clean this up and let's get started, and we're going to begin by doing a linear spring modeling stiffness, so no unloaded length. Let's start by drawing a diagram of the system. So we're going to do a mass, and there's a spring attached to it. Now, I'm going to say that this spring represents some kind of stiffness, and we're going to model it without any unloaded length. And then we can just come back and we can use the same diagram to model a problem with an unloaded length. So what I'm actually going to do is, this is how I like to do my spring diagrams. I'm going to separate these, and I'm going to draw actually a free body diagram for these. Now, in this video, I'm not going to dig too much into the theory of the free body diagram or how to come up with the correct spring terms. You can look at, again, look at the video for the spring mass damper, and I go into the details there. So for now, let's say that we have a point on this block, point A, and just to make it a little clearer, let's put point A on the bottom where the spring attaches. So point A is on bottom. We're tracking the motion of this with Q in the y hat in direction. So there is some point N that exists and there is some inertial frame. Now, we have to assume some kind of direction on the spring. I'm going to apply the spring forces in these directions. So currently we're assuming that the spring has been stretched. So the spring is under tension, and that means it is pulling the block down. Now, under these conditions, again, watch the video on spring mass damper. Under these conditions, the spring force is going to equal K times the variable Q. And there's going to be a positive relationship between those. So we have a force and we have a position. That means we can come at this from definition of work. So dW is going to equal the force dotted with dP. So let's take these two and let's write them in the form we need for here. So first of all, the force. Well, I wrote it as a scalar, but forces are vector. And in this problem, based off of how I made my assumptions, notice the force term is KQ, but I have applied it in a negative direction. So we're going to write our force as KQ in the negative y hat in. And of course, we can just take the negative out. This is negative KQ y hat in. Next, we have a position vector. So dP, this is going to equal, you can just distribute the differential. So the dq in the y hat in, and of course y hat in is constant, so we do not have to do product rule. Let's take these, let's put them into the work equation. So dW is going to equal negative KQ y hat in dotted with dQ y hat in. Of course, the dot product is going to turn this into a scalar equation for us. dW is negative KQ dQ. Now, we don't actually want the work done, we want the potential energy expression. So again, I'm going to use the Greek letter phi, and this is the potential of a spring, and this is the negative of dW. So d phi is going to equal negative of this, so the negatives cancel, KQ dQ. And we can, of course, find that potential term through integration. So we're going to integrate d phi. That means we're going to integrate the right-hand side as well. So the integral of KQ dQ. K is a constant, bring that out. Just as a side note, if you were doing a nonlinear spring, these K terms, maybe it's K times Q squared, maybe it's K times Q cubed, maybe K itself is a function of Q, etc. So this is the point where your nonlinear springs become a little different. But we can integrate this very easily. The integral of that is going to be 1/2 KQ squared. And don't forget, there is the integration constant. Now, in this case, what do we do with the integration constant? Recall in this problem, we're saying that this is a spring without any unloaded length. That means the potential when Q equals 0, then the potential is equal to 0. So if we take this expression, we plug in a 0 for Q, and then we set it equal to 0. Okay, that means that 0 equals A. All right. So your potential energy expression for a spring without an unloaded length, 1/2 kq squared, where k is your spring constant. Now, interesting thing to take note, this does have a form similar to kinetic energy, and of course that comes out of the fact that, that we're integrating. Other interesting stuff though, you do see something similar if you look at energy stored in a magnetic field. That is going to be 1/2 Li squared. So L being the inductance and I being the current. And you can generate this potential term from a similar process. We could start with work, and we could do the force in that electric, that EM field, and we can dot it with change in some position. We can come up with these same expressions. So oftentimes when you see something like this, the 1/2 raised to something squared, usually this is coming out of integration. Okay, next. So this was the spring with no unloaded length. So how does this change if we have a spring with an unloaded length? So let's go back to our diagram, and I'm going to make the same assumptions about the directions of these, and our spring force this time is now equal to this. It's K times Q minus, and I'm going to write it as Q sub naught. So this Q sub naught, this is your unloaded length. Okay, so what changes? We just have to take that force, right, and we put that into the work expression. So dW is going to equal, again, the force is acting down, so I'm going to go ahead and write this as negative K Q minus Q naught in the y hat in direction, dotted with dq in the y hat in direction. Okay, let's just move on to the next steps. We know that the energy is going to equal the integral of negative k q minus q naught times dq. So I skipped a few steps in the middle, but again, we know that integrating this yields the work, and the negative of that is, oh, that's right, There we go. There we go. Got to lose the negative. Okay. So we want to integrate this. How do we do it? Well, consider you could just distribute the k, and we could bring this into two different integrals. But this is going to equal 1/2 k q squared minus k times q naught q plus the integration constant. Now, this term in the middle, where did this come from? K is a constant, q naught is a constant, and then that makes it just a constant multiplied by the dq. So you end up with a q. All right, so what are we going to do with the integration constant this time? So now, if you take our potential expression and we set q equal to q naught, that is now equal to 0. So this q equals q naught, again, q naught is the unloaded length. So if your q variable equals the unloaded length, that means it's unloaded and it's storing no energy. So q at, phi, the energy at q equals q naught, this is equal to 0, and then the expression is now 1/2 k q naught squared minus k. Notice that when q becomes q naught, this is k q squared plus a, q naught squared. There we go. So what are we going to do? How do we get rid of that integration constant this time? Well, we can subtract these, right? These are both k q naught squareds, and you've got a positive 1/2 and a negative 1, so that's going to yield a negative 1/2, and then we move it to the other side. So a equals 1/2 k q naught squared. All right, we're not quite done yet. So I'm going to take the potential function, I'm going to rewrite it with this new a value, so 1/2 k q squared minus k q q naught plus 1/2 k q naught squared. Okay. So what can we do next? Well, let's say we factor out a 1/2. And we can factor out the k. So 1/2 k, that's going to yield q squared minus 2, right? If you're pulling a 1/2 out of the middle term, there's a 2. Q naught q plus q naught squared. And we can actually rewrite this term in the middle such that our potential is 1/2 k times q minus q naught squared. And that's it. This is how you construct your potential energy expressions for springs. So think of the more difficult cases. What if you had multiple blocks on top of each other, etc.? However many of these blocks that you have in this, this chain of springs, you come up with your spring, an expression for the spring force, and in this case, it's going to be a function of 2 moving bodies. So it's going to have a Q1 and a Q2 in it, and then you take that, you put it into your expression, you integrate, you can find the energy now. Okay. Now, what I expect for the students that are taking the dynamics class, what I expect them to be able to do, I expect that you know this. I'm not going to ask you to derive these things on an exam or a homework, but you should be capable of coming up with these types of, or just remembering these types of potential expressions. Okay, so that's it for this video. Take care of yourself, and I'll see you around.